Good morning, hello! Happy Sunday, happy Halloween, everyone. I'm sorry I'm not in costume. I had some thoughts on what I wanted to do, but then just things got a little bit crazy and I wasn't able to do it. So maybe next year? But besides that, I'm happy I'm able to stream today. We're gonna be doing all of that stuff. Let's see, we're doing the exploring the Rust Standard Library. That's what we're doing. So last let's see, what was it? Last week, sometime over a couple of days, there was the GitHub Universe, which is sort of like a conference for GitHub type stuff. They announced some new things for the code spaces, which is really cool because I've been using this a lot recently and I've been liking it a lot. And apparently now you can manage code spaces through the GitHub command line interface, the CLI. And I haven't really played with it too much, but apparently you can SSH into them now. So if you want to just do, no VS Code whatsoever, you can still work with code spaces and actually get into them and do all the things, which is actually really awesome. Sometime I might want to do that because I can imagine setting up dot files and doing like Vim and other interesting things inside of them. That might be another project. But today we're continuing on with the, what is it? The F-32s, I think, is where we were at. Yeah, F-32s here. So let's go find that. Yeah, here we're on F-32s. We got down to, I think, tan. Oh, these aren't in order of what they're defined in here. That's interesting. Okay, so here's tan. We're only like a quarter of the way through F-32s. Now, I think, I'm not completely certain, but I'm pretty sure that all the floats have the same methods on them. And the only real difference is like how, what degree of like, what's the right word for it? How accurate, how many decimal points we can get out of it. So like we have F64, we have F32, there's F8. I think, is there an F128? I don't remember. I know there are integers of that length, of that size. But it could be interesting to sort of like just double check. This might be going through all of the floats at once. So we just did tan. And so now we're going on to assign. I don't know how much like actually like doing like little test things, how much that's actually worthwhile for us, because like this is just like the math of like, hey, it has these things, which is interesting to know. Computes the arcsign of a number, returns values in radians in the range. Okay, so the big deal here is that you get radians. Or nan, okay. Oh, and it's a normalized number, so it's between -1 and 1, which is great because that means you could then scale it up if you really want to. The arc cosine of a number. And let's actually take a look at what I had done in here. I guess like we had figured out what these are supposed to be, and then we were sort of like trying it. I don't know if I want to continue doing this too much. Let's see. So the arc cosine of the number. So that's the opposite of cosine, right? So where cosine would be at the top of the, what is that called? When you're at the top of the wave. Oh, I forgot the term for it. But then it goes down to the bottom, and then I think that's the arc cosine. It's the opposite, maybe. We can actually get both the cosine and arc cosine and take a look at them together. So here, I'm gonna remove a bunch of these. In fact, I don't think we need these implementations at all. I'm just gonna use this as my scratch pad. Okay, so let's say we have a number 10. So our number, which is going to be an F32, is equal to 10, 0. And if I want to get a cosine of that, so we're going to debug number dot cosine, and I also want to debug number dot a cosine. Actually, I don't want to do it in here. I want to use this thing. Oh, the a cosine is nan. Okay. Let's compute. Okay, so nan if the number is outside the range of -1 to 1. Okay, so I want to make sure that you are in like 0.5 or something like that. Okay, so we can see here's our cosine is 0.8 and our a cosine is 1.04. I don't know if that's like opposites or not, but that is interesting to see. Like we can definitely take cosine of any number, but not a cosine. But I don't remember cosine versus not cosine very much. Limacode, hello and good morning. How are you doing today? It has been a while, but also I've not been able to stream too many times recently. Good old lazy Sunday. Yes, it is. It is also in radians too, which is, I don't think it takes it in radians, right? It's just the return value is in radians. It is interesting though that the number, when they talk about the number is outside the range of -1 to 1, that's the number you're getting the a cosine of, which can't be degrees. So that must be, I don't know what that, well, I mean, it's my lack of math skills. I don't really know when to use it. And it's the same for all of these things, like with atan and atan2. Now the atan2, I remember, is how you can get like the direction and velocity towards another x. So atan computes the arctangent of a number. Okay, so we give that. So basically these are all like based on pi. So we're getting like a location of a circle, right? Like where we're pointing on a circle or where around the radius we are, which is interesting. Those are all these things that like I like to know, but then I'd never remember them. atan2 computes the 4 quadrants. It's like they show this, but that doesn't really, I don't know. Positive angles, 135 degree counterclockwise. This is, oh, that's 3 pi, yeah. Oh man, I did one game, and I think I mentioned it last time, where I had like a ship and I wanted to click somewhere and have it like rotate towards that position and then move towards it. And I didn't know the tricks to use with vectors at that time. So instead, I looked up and found the raw math for it, which was using ATAN 2. And I wasn't doing this in Rust at the time. I was doing it in Lua. That was super interesting. I probably still have that code in GitHub, because I was doing it on stream too. This was a very long time ago. You can move the point, multiplying by 10x, and then doing y mod 10 to the x. Oh, okay. So we start with like 0 dot something, so it's normalized, and then we move that out by taking 10 to the whatever it is factor. Okay, that works. Also, Perhine, I can never remember. Perhine, I think. Good morning. Oh, sine and cosine together. So this is interesting. In case you want both sine and cosine, you can get both them at the same exact time. It returns a tuple of both numbers. Obviously sine first and cosine second. That's nice. Oh, I'm not necessarily trying to do anything. We're splunking through the standard library, and so we're on floats right now. And so there's tons of math-based stuff here, which is like, I don't really, like, I'm not that great at math. I never, let's see. It's actually one of the reasons why I didn't get that far into like computer science, is like I didn't do too much math of it. And I ended up like dropping out for a multitude of reasons. But like the logic-based math, I was great at. For going like doing calculus type stuff, so I was like, yeah, I'm not there. Like oftentimes I only like pull these out when I'm essentially told by a library or something else that I need to have it. Otherwise, the only maths I really learned and have like internalized are vector maths and like matrix math, which is interesting because some people consider that harder. But to me, memorizing when to use these and what these really are is harder for me. So I'm better in arithmetics than in algebra? I guess so, yeah. Oh, geometry. Yeah, I guess that could is matrix math in the geometry section. It's been so long since I took any of those classes that I forgot like what their specialties are. Okay, so exp m1 so returns e to the whatever it is -1 in a way that is accurate even if the number is close to 0. So that's interesting. So I know that E is a number, right? E is a special number, and I forget what that means. Can I look up what E is? The mathematical constant. Oh, it's Euler's number. E is a mathematical constant approximately equal to 2.71828. Okay. So, Gareth Hubble, hello. We're doing good, I think. How are you doing? Okay, so it's around a 2. Okay, so it's 2.71828. It's calculated as the sum of infinite series. Oh, interesting. Like 1 over 1, 1 over 1 times 2, 1 over 1 times 2 times 3. Yeah, this I remember because like I at one point in time I tried to get better at math and programming at the same time by doing Project Euler, and I got lost really fast. Like I didn't want to just look up the algorithms, but I couldn't get like past the first page without having to start doing that, and so I ended up giving up. But yeah, a lot of that stuff is like these type of magic stuff, which is it's kind of fun to sort of like graph out, and I think I like the idea of like visualizing it too. But what I'm interested in here is, okay, the natural exponential function, so this is e to the x, is unique function f that equals its own derivative and satisfies the equation f(0) is equal to 1. Okay. But here, if we have e, the other equation is famous. I am not surprised. I mean, he was a famous mathematician, right? So, I mean, isn't this is one of the many things that made him famous, I'm sure. So what I want to do is I want to try to do this manually, because the thing that this documentation says that like pops out to me is that it's accurate even if the number is close to 0. So we are going to go e to the and then something. So let's say I do e to the let's start with like 10. So let's do let exponent is going to be equal to 10. Sure, we'll do 10.0 f32. We'll do f32s because that's what's going to happen when we do it the other way. So I just want to make sure we get it right first. So now I want to do let e is equal to, I think it's going to be f32. Oh, it's like standard f32. Is it epsilon? No. Euler's number. Epsilon is not right. The integral is e to the x plus c. Now, can I find, like, there's const. Oh, e, there it is. Okay, so here's e. So if I want to do this manually, and I want to say, let's do like 0.0.001, because I think that's what, like, close to 0. So I want to do e to the, so e dot I want to the power, so pow f exponent we'll get that, and we'll debug what the result is. Okay, so we're able to get this number. So 1.0010005. Epsilon is the smallest non-zero number. Ooh, okay, that's good to know too. Yeah, I remember, like, we looked at the largest one and I forgot what that was called. But that's good to know too. Okay, so this is if we do this 0001. But what if I now try to do debug of exponent dot what? Oh, is that exp_m1? Let's see if we get the same thing. No, they're just subtly different here. And that's what it's trying to say, is that this is This is much more accurate, supposedly, than just doing it myself. So we can see, okay, the one we did up here, that is, oh, well, this is fascinating. It's 1.0010005, and this one is 0.001005002. That's like, did I do this wrong to get the one there? Oh wait, it's -1. I forgot, there's a -1. Okay, that will make it accurate. Okay, so that changes things. So it's now 0.0010005.236, whereas this is now 002. And I wonder if they continue to get farther apart over time. So let's imagine that we're starting, I don't know, yeah, I don't know why it would be useful, but I noticed that this function literally does a -1 in it. So to normalize it, maybe? I mean, if they're always just between 1 and like 1 and 2, I don't know. It's a good question of like why. For very small x, e to the x is approximately 1 plus x squared divided by 2. Interesting, okay. So this is like manually doing it. Oh, right, because they're calculating e yourself too, is what this is doing. But we have e. Now, I'm curious of like how at what point. So let's do like 10.0. What happened? Why are you upset? Rest analyzer. Restart. Give me the run. No? You won't let me run anymore? Did I screw this up somehow? I don't see like an error or a warning. Okay, I guess I'll just do the old-fashioned way. Cargo run, example, primitive F32. Okay, so even with a 10.0, we have just a subtle difference here, like 22025, 22025, but then a 459 for 465. So like off by 0.004? 0.006? See, what is that? 46145 6.006. Thank you, Gareth, for correcting my terrible math. Not off by very much, but still off by a tiny bit. And I wonder if we go to like 100, that should make it even less off, right? Oh, infinity. Okay, so I can't do that. Now I'm curious, in F64s, is that big enough of a number that this works? Yes, it is. Okay. This is a large number. 268. Would it be worth benchmarking two methods of working out to look at performance trade-offs? I don't know. They're both like super fast. I don't know how I don't know how much that would help out. Like I don't know how because it would be a micro optimization, right? But I'm guessing that in this point of time we're looking at accuracy over speed usually is what you want, but I don't know. I've not been in a position where I need to do these type of maths, but I wonder is this type of math helpful for doing like physics calculations? Because in that case, accuracy probably is way more important than speed. 365 minus 212 or 356 212. Yeah. One of the things I want to do is change these debugs to print lines. And then we should have them on the same line, like the same here. So you can see the same number of digits. So it is right here, this 212 and 356. So this feels like doing it ourselves, the larger the number it gets. Did I read this backwards? No, I didn't read this backwards. Returns e in a way that's accurate even if the number is close to 0. However, it's probably accurate even when the number is farther away from 0 too. No. No. Come on, give me the right keyboard. Ah. There. Okay. Sorry about that. Let's see. Poly Insecure, hello. You can see being used in games. You're thinking that it could be used in something like fast inverse square root in use. Is that what Quake did? Because I know they did something in that area. But I never actually watched the video, because I know they have there's a cool YouTube video which talks about it. And I have it in a list of things eventually to watch, but I've never gotten around to it. Mostly because this type of math usually makes me eventually go cross-eyed and was I don't understand what's going on, but it's really cool, but I don't understand what's going on. Yeah, the fast inverse square root was a John Carmack thing for Quake. Okay, so that is exactly what we're thinking it was. Okay, so the other things I was thinking about it was for really large scale simulations, like Kerbal Space Program, because the farther, so Kerbal, the planet, was the center of the usually you call them the world, right? But in that case, the center of the universe or the galaxy or the solar system, whatever that however they implemented it in I don't know if they use an ECS system or not, but Kerbal, the center of Kerbal is 0, 0. Then the farther away you got from it, that floating point number started getting pretty crazily high, and I never played far enough into the game to get really far away from Kerbal, but I saw some YouTube videos of people playing where the farther you get, you make a tiny little adjustment and you start jumping all over the place. And that's, I think, due to little errors in floating point math that far away from the center. And I wonder if like doing things like, I wonder if this can somehow help in accuracy there, but I don't know. I don't know enough to like know. Ooh, well that was super fast. Thank you, Gareth, for reporting that. Also, thank you, Twitch, for reacting to that extremely quickly. It must be getting a lot of reports right now. It's probably hitting all of the accounts. Now, so at 100, it's like super off on F64s. Is there a point in time? It's like one thing I want to do. So here we have exponent, we have E. So let's start with 1. Let's then do reduce by is going to be something like 0.01, let's say. So down by 0.01 every single time. Let's do a infinite loop here. And I want to then grab our result. We're going to get the result. We're going to print it out. And then we're going to change our exponent. So you need to be mutable. So exponent minus equals reduce by, and then we continue on, and then let's like pause just a tiny second, maybe. I don't know how many of these we want to do. Oh, let's see what it. Let's see. Let our duration for sleeping. Lord Mist, hello. Good morning. Yes, I have been exploring it for a pretty long time. Absolutely. Like it's a small standard library compared to other languages, but like there's a lot of things attached to other stuff. So we're taking a look at floating point numbers right now, which is interesting because there's a lot of things here which I haven't even like considered or thought of like looking into before. So for example, this this exp M1, which I guess the M1 is -1, right? I guess that makes sense. I'm kind of surprised that it's exp or e to the exponent. Okay, that I would not realize what that's what it does from this. But okay, we do that. I want to sleep by, or like pause amount. So pause duration. Let's get a duration. Okay, so Rust Analyzer failed again. No, you don't know how to get me a duration? Okay, what is it? Standard standard time? Let's go find duration. Yeah, okay, so it's standard time duration. Standard time duration. I think there's like a from. We can do from seconds. From. Let's do milliseconds. From millis. Okay, so from Millies. Let's do like a quarter of a second, so 250. That'll give us that, and then we can sleep, which is thread sleep by something. I'm kind of sad that Rust Analyzer is just like completely given up. I don't know why. It was working earlier. It just is like, yeah, we don't like it. Kind of works a little bit, and then is like, yeah, we're done. Sleep. So let's see. Standard thread sleep, and then a duration. Okay, so standard thread sleep. We give it this pause duration, and then that will make it like halt and wait. So now if we run this, it is an infinite loop, but at least it's not going to be that fast, and we can see these numbers change. Perhaps to make it a little bit, just a tiny bit easier, let's give these a little bit some labels. So this will be the sort of like the one we do manually. So manual. And this is the X M1. Perfect, that's the same number of characters. And let's also we'll give it that. So now when we run this, now we can see these coming in like that, and we can see the numbers changing. They're definitely not that close to each other, but I wonder if they become closer to each other the closer to zero we get. Would a Control-Shift-P reload window help? That might be. You know, it's like, yes, maybe one of the two. Epic Blarg, hello. Joan Ben on Rust Station recently noted that Rust Standard Library is small but deep. Yeah, I totally agree with that. Like how option and result have a surprising number of methods. Absolutely, yes. Can we stick those numbers in a CSV and graph them? You know what we can do? We haven't, so we can, if you don't all mind a little tangent, we can play with this with, and then also, yeah, we can graph them. You know, something that I haven't done. Tangents are fun too. I know, we looked at Tan. There is a crates.io. There is a charting life. There's a charting crate. You know, this used to have dark mode for me, and like it stopped working, I think, or did I turn it off by accident? Oh, I turned it off. That's why. So we have a charting library here. We might be able to play with this. Use live.rs. I mean, it's the same thing. I mean, it looks at the same stuff. I guess it just has a different. Oh, you've never seen live.rs? Okay, so it's like a different front end to crates.io, except it builds once a day, twice a day. So it's basically just a different pattern. So let me turn off dark mode on here so you can sort of like see what it looks like normally. Dark mode by default. This is what it looks like. We can go to the crate. No, wait. Chart. Inspired by D3. That's good. A terminal plotting library? Wait, that could be cool. Oh, I like this. All right, let's try this one. It's very fast. It builds like once or twice a day. So if you do, if something got updated and you check for it like literally seconds or minutes or even hours later, it may not be there. You may have to wait a day or two. So Crates is like always up to date because it rebuilds every single time that somebody pushes a crate. But this just like reads from the database that Charts has, or sorry, that Crates has. I'm now getting confused by everything that starts with C. But okay, let's try this. I want to create like a, I want to see if we can like plot this out. And this could be like pretty interesting. And we can do some of the other, like the other math things for it too. Oh no, you might be a day behind. I know, like the end result is like, it doesn't really matter, right? Because you can still go to the real documentation from it. Like the links to the actual documentation are just the links to the documentation. So, okay, so let's see how we're going to use this. Let's come back into here. We can actually do this as a real project. So we have this source in lib. Let's actually give ourselves a main. Come on, no find. You can just do things in here. Okay, so using it as a library, or actually, you know what? We can do this inside of inside the example, can't we? Okay, so using it as a library, use text plots. Okay, so let's bring you over here. You go over here. What's the difference? Why are you somehow working out? Did I create like a different file somehow? Yeah, these are two different files as far as it. So primitive F32, they're named the same thing. This is examples, primitive F32, and this is okay, everybody closed. Oh, okay, it works again. Yeah, I don't know why, but Rust Analyzer is up again. Okay, let's reset this. What we're gonna do is we're going to use text plots. Oh, we have to actually pull this in too. Toml. Okay, so we're gonna want this chart, the plot, and the shape. I'm using, I think, a default one. What theme am I? I don't remember how to look at the actual theme I'm using. But I think it's like, I don't know if it's using the default one or if it's using the one in the code space. It's so like, I haven't looked into too much like how to I think I can like have them synced, but I haven't done that yet. Okay, so here we have text plots. Okay, we're gonna have our function main. Okay, so let's try this one first. So we're gonna do a chart, default, do a line plot. Okay, so that's interesting. We're gonna have this shape continuous box new, and then we give it the algorithm inside of there. So a reference to a shape continuous box new. Then we give it a we give it closure. So we take in X. So we let's just do the sign first, just to make sure we got this working. So we're going to get x.sign divided by x. We do u, and then we'll do a dot display, and that's it. Nice and simple. And if we run u, let's see if this works. Code spaces. Yeah, so I got part as soon as they announced it. I had applied for the beta and I got in, which is why I can use it for free here. At my work, I liked it enough that I convinced my boss that or CTO, same thing. Hey, let's try using this as like a development environment, because when we onboard people, it's gonna be so much easier than like all this other stuff. We don't have to buy everybody the most expensive computers anymore. And it's been working out pretty well. Codespaces is a VPS essentially that runs, it's like a containerized VPS that you can spin up per account, like per repo essentially. So if I come over here to Remote Explorer, wait, no, wrong one. To this one here, you can see I have these different code spaces, and it's basically a VPS per repo, and they charge you, if you pay for it, per second that it's running. But they don't charge you for it to have there. They charge for space that you're using, but it's incredibly cheap space-wise. And so I'm able to say like, hey, let's open these things up and just like go, and you know what was days to like get somebody set up on the system is now like minutes, which is really awesome. Oh yeah, and it works on iPad. I did test that out. I was able to open it up, heck, on my phone. You have to have a keyboard to really make it like useful, but it works. It works really well. You hate that cloud computing bad? I'm sorry, but I like it because it allows me to have more things done for my team. Okay, so here we go. We have a terminal-based plot. This is awesome. I love this. Okay, so now let's try our algorithm again. So our algorithm is going to be this thing that we pass in here. So interesting enough, this is continuous. So it's handing us a new number, and then we're going to plot it, right? So I guess continuous is giving us a new number over time, right? Can I control what that is? Where's our documentation? Okay, so you have like points, lines, steps, and bars, but we're just doing like what does it mean? Wrong one. You go down. Okay, so it's continuous from -10 through 10. And -0.2 through 1. And I guess each one of these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 on each side. So what is that? 0.5 for each one, I think. Oh, and Lord Mist, you missed it, but another thing that Codespaces recently announced is the ability to SSH into them. So you can now use Codespaces without having to use VS Code, which is nice because now that gives you that option of just like going in and using Vim. Okay, so let's try, we're gonna take this number and we're gonna do now x dot xm1 and we're gonna run u. So that's what it looks like. It's like super small and then it becomes really huge really fast. I wonder if I can change this. I also wonder, can I like graph two things against each other? Oh yeah, I can do two line plots. Okay, so I don't know. It's a good question. So let's do this. So we have line plot, and then we're gonna do another line plot. That's gonna be a shape, continuous, box new. We get our X, and we're gonna, okay, so this is gonna be X. So this is a e to the X. So it's gonna be standard F32 const e dot pow f to the X minus 1. So this is essentially the exact same thing as what's happening here in this different line plot. So if we now run this, they're so close to each other that you can't see the difference. I think that's what we're seeing. Can I, looks like we can do a color line plot. Line color plot. Okay, so we give the shape and then a color, which is an RGB8. So after this, so an RGB8, U8, so RGB. Oh, okay. Red, let's just make this red. So 250, 256. Wait, is it 258? Zero, 250, 258, 256, 255. I was like, I've forgotten everything about numbers. Okay, so we have a red and then we have the white. No, I don't. Let's okay. On your example here, not found in scope. I thought you would have pulled that in automatically. How do you know what this is? Okay. So RGB. You're not in here. Okay. Go to RGB. No, here it is. Okay, pubstruct you. You're in. Oh, we need to pull in this RGB. Or it's re-exported. Are you re-exported? Wait, how can I see? There's usually a section that says what's re-exported, right? Did they change that? Oh, their box to avoid generic cell. Yeah, okay, that makes a lot of sense. Let's see. So I can't find you because you're not in the documentation, but you're technically in there, but maybe you're not re-exported, which means I need to go find. Oh. We need to go find RGB. I think this is it. Yeah, okay. This is gonna be it. So just RGB. Then you are gonna be RGB in here. So use RGB, RGB. Okay. Let's try you now. I think they're too similar to each other. Can I change? Can I make this one down to the bottom? And then that should make the red stand out on top. Okay, yeah. So they're basically overlying each other. Exactly. Coding Garden fan, hello. Yeah, the white line goes directly over. In this case, the red line goes directly over, except over here. It's like subtle differences. So now what I want to do is change this. So can I, where are you? This is, okay, chart new. Ooh, okay, so we can do chart new and then give it, okay, there we go. So what are you, we're gonna figure you out. So we're doing a chart default. So we're gonna do a chart new. You take in the width and the height. Are you pixels or are you lines? I have no idea what my width and height is. Let's try like 100 by 50. And then you are this X min. So let's do like -1 and 1. Okay. And if we run you, it's still so close to each other, even as it's like, even with a smaller number. How about -0.01 and like 0.01? No, it's like, even when I'm getting that, they're still so close to each other from the calculations. It's like the plots is too hard for it to see. So I'm not exactly sure how I can display this outside of here. The width and height is pretty nice. I wonder if I can go like a lot more. Let's try like 80, 120 and 80. Oh, I have so much more room over here. I can almost double that. I wonder if I can go to 200. Let's see. 60 is probably good enough for height. X-Men, we kind of want to do... We can see some like the lack of the overlap near 0 here. So if we want to go near 0, then I guess we continue to bring this down. But even when I go like close to it, it's still really close. So I guess like that's pretty cool that we can get that. Like it's oh, here we go. It's that accurate, but now we can see the differences. So this is fascinating. When I do that myself, I take e to the power of whatever. It just does this jump here, whereas the exp, the method that we use is an actual curved line. So it actually is accurate that you can see here is like, it's definitely accurate. It's not accurate at all when we're trying to go with like really small numbers. But you saw how small the numbers I had to get for this. It's pretty crazy. Also, this library is pretty cool. I like it. This is called Text Plots, in case any of you want to play with it. Here is the documentation for that. I like it. I think we can do some more stuff with it. Coming back to our sort of standard library, spelunking. So we were just looking at XM1, which is this e to the self minus 1. Some of you was asking something else that we can do. Oh, do x to the 10 to the second. Okay, yeah, we can try that. See how big of a numbers we can get. We might have to go to F64s for those. But here, let's we'll get rid of this line color plot here. And we can then do, so what is this? This is going to be our, I want X-min to be negative 10.0, X-max to be 10.0. And we're going to do X times 10. We're going to take that and go pow I2. And let's see what we get from this. I mean, it seems to handle this just fine. We could probably make it go even bigger. Let's make it go crazy bigger. I mean, it's handling it. Okay, so we have the natural logarithms more accurately than if operations were performed separately. Okay, so this is this 1 plus 1? 1 plus? Oh, x squared, x, okay. X to x to x. Yeah, let's try that. So we'll do... So this is going to be x dot pow f x. I think it's then pow f x here. Otherwise, it would be to the x to the x to the x rising, which could also be interesting. And it does bind to the right. You're right. So that could be interesting. Also, it doesn't like this. What did I do wrong? I like deleted something. Yellow, blue, purple. Okay, I'm missing one of these. Yeah, now it just gets at this really, really large number, and it's just like, okay, we're fine. Straight line. Yeah, okay, so I think we need to do what you're suggesting. Is we're gonna do x dot powf x dot powf x dot powf x. Still, it's like, we're fine, huge number. Just straight up as far as it's concerned. So it is nice to see that they have these methods here that are extremely accurate when things get like super small or super large. Oh yeah, I didn't notice you only had two. I put in three. Oops. That the third one makes it go insane. A hyperbolic sine function. Oh, and here we're using this epsilon constant, which is what we learned earlier was like the smallest possible number that we get for a float. So a sine h, I'm curious what a sine h looks like. So x dot sine h. This is what that looks like. Now, if we want to plot a normal sine over that, line plot color, have this shape, continuous, x dot sine. Can I just say like red? No. Is there like a new? Yes, new. Okay, so we'll do 5 0 0. Our sine is like so small compared to this hyperbolic. It's basically staying at this 0 here. So that's interesting. Oh yeah, we can go from -1 to 1. We can definitely do that. So we can see it's starting to turn back up here for this sine wave. So it's It's very like a very slow going up and down like that. Whereas this other one is just heading off. And we know that it's heading off to go into the infinite down and up on each side. Again, I don't really know when to use like a lot of these. And apparently, okay, we have hyperbolic cosine as well, and tangent, and a sine, and a cosine, and a tangent. Okay, so now on to implementations. Okay, so we have radix. The radix are basically the internal representation of F32. So this is a const radix, which is a U32. Is that just 0? A sine is the opposite sign. Yeah, I know that much, but I don't know why I would want to when to pull it out. Usually I just like wait until like hey, I need to do this thing. Google how to do it, and somebody says use a tan 2 or use a cosine. I'm like, okay, I'll use a cosine, and then I still don't know when to use it because I didn't really understand why it's happening. Yeah, it's like the side effect of not like I care more about the programming side of it usually than the math side of it. So I never really get deep enough into like understand. Okay, so the radix are base of the internal representation of F32. So is that 0? No, it's 2. 2? Or, okay, the radix are base of internal representation of F32. Is that like one on each side of the decimal points? What's a radix? Can we search this? In a positional numeral system, the radix or base is the number of unique digits, including the digit 0, used to represent numbers. So 0.0. So the base, so like 0 is represented by 2 digits, 0.0. Is that right? For example, the decimal denary system, the most common system used today, the radix base number is 10 because it uses the 10 digits from 0 through 9. In any standard, oh wait, so then is it 2 because it's binary? Binary, okay, so binary. Used internally by nearly all computers is base 2, so it's binary. So they're storing it binary internally. That's what we're reading in here. Mantissa digits, the number of significant digits in base 2 is 24. What does significant mean in this case? Is that to the left of the decimal or to the right or both? Like none of this information is gonna like change how I program, but it's like fascinating. Manta said, there it is. The significant, significant, wait it. Is this just a typo? The number 123.45 can be represented as decimal floating point number with the integer 12345 as the significand and a 10 to the negative 2 power term called characteristics. Okay, so basically the significand. Now this is significand. I'm not looking at the right thing. Is the same thing. That's what it's pointing to here. Yeah. Interesting. So it's stored like that internally. For a normalized number, the most significant digit is always non-zero. Okay. But if we take a look at what we have here. Okay, so in base 2, it is 24 is the number here. Wikipedia doesn't explain things really well. The Wikipedia, what I sort of understand is Wikipedia explains things if you already know, for math stuff, if you already know the math a little bit, at least a little bit. Same thing with algorithms, same thing with everything else. Okay, so this is like 10 to the third. So is the significand this number here? 24, like up to 24 digits for an F32 after the decimal point. So 56 and 0.0000056 are both representations that have two significant figures. Okay, so I can have 24 significant figures in base 2. That means I can have 24 ones. Interesting. Okay, so, and that's the reason, is that the reason why my max numbers can change so much depending upon what the number is? 24 digits after the first one. So imagining that if we have a number like 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So all of these can be ones? Not 24 ones, 24 digits after the first one. So we can go like this. But if I add in like 1 here, I think we lose one of these. And now it can only be like that. I think I'm misunderstanding this. This doesn't seem right. For that 0.000202, 3 significant digits. Oh, and you know what the other thing is? We're talking about binary, and I'm writing this out in decimal, which is not helpful. Okay, so everything after the right when it starts typing is significant. And I can have significant to the left of the decimal and significant to the right of the decimal. Or is it just starting here, everything is significant after this? Interesting, okay. So I can have 24 binary significant. What is 24? What is it like? 0b. Let number equals. Was it like 0b? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, something like that. So that would be hundreds, thousands, 16,777,215. And there's a way to represent this in F32, right? But I don't remember how to like get them as the decimal points, because I don't think I can do like 0 dot that, or maybe no, that's not gonna work. One of the bits has to be flipped to tell it that it's like what type it is, right? And like where the decimal point happens. I don't know where that is though. So that's interesting. But that's not really super helpful here. And I think that's misleading as to like what the actual values are, because I can have like 0, 0, 0, 0 and then start the significant digits after that. Approximate number of significant digits in base 10. Well, I guess if we looked a little bit further into it, we'd see, hey, we can get 6 digits in base 10. Okay, so we have epsilon, which is the smallest number that we can get. This is kind of fascinating. Now, I calculated this like this is the Rust documentation on the website. I wonder if I redid the documentation locally, if I would end up getting a different number here, based upon the architecture of the CPU and everything else that we're going with. Hi. Hey, kitty cat. You don't wanna hang out? You wanna go play in the closet or just sit on the floor? I don't have any food for you, sorry. I should get some snacks in here. He would love us a lot more. I've also thought about getting one of his favorite toys down here, and then I can get a camera pointing at this other room. We can do like a break time for getting Zibby to jump around. That could be interesting. Okay, so we have epsilon, which is the difference between 1 and the next larger representable number, and then min, which is the smallest finite F32 value. And then min positive, which is the smallest positive normal value, which I wonder, that's not going to be the same as 0 plus epsilon, right? So there's a lot of these that we can use to sort of like determine, are we checking between like too small of numbers? It's like if we're doing some kind of math for a game and we're like, hey, are you like, are you between these two numbers? If you are, let's just like assume you're here. That might be what we use it for. Largest finite F32 value is this. One greater than the minimum possible normal value power of 2 exponent, which just happens to be negative 125. That's interesting. Minimum possible normal power of 10 exponents. It's like all these sort of numbers that we have here are interesting to work with. I think we tried to use some of them during one of the I don't know, one of the games or simulations that we made. I don't know if I did it correctly. Now, non is interesting. It's a const, which I think just is non, right? Now, this is fascinating. The way they create the const non is to do a divide by 0 to create infinity, which is not a number. And then they do negative infinity. Oh no, they do infinity and negative infinity almost the same way. Interesting, okay. Is non as interesting because so like we learned this last time, but nan or non is this has the same sort of like weirdness that JavaScript and some other language has with non. If any of you have not seen like the WAT have any of you seen like the WAT conference talk on JavaScript? It's really fascinating to sort of see. And it drives a lot of people crazy when you can say things like, is it non equals non? And I think this is false. Not a number does not equal not a number, which is like, what is going on? Which is why we have in JavaScript these is non. But unfortunately, or fortunately, depending upon what side you're on, if we take a look at debug and we look at standard F32 nan, yes, I know, Clippy is yelling at me. However, it's also false. And that's the reason why we have to use isnan here. So there is a standard F32 non dot isnan, and this will be true. And you can get nan really easily by doing things like dividing by 0 or some other like math that like basically turns it into not a number instead of throwing an error, crashing your app, which like we've run into that problem before where we're like converting numbers and using them. And then like at some point in time, the number conversion failed, we got non, and then bad things happened. The app still worked, it just didn't work the way we expected it to. Is infinite also is nice to know, because I guess infinite is not going to be equal to infinite because it might be different things. Like what if it's negative infinity? What if it's positive infinity? And I guess the value of infinity could be different too. Interesting, we can also do is finite, meaning that, oh, is finite returns true if this number is neither infinite nor non. So if you don't know which one it might be, is finite is probably the way to go. I kind of like this one more. Subnormal. In computer science, like, subnormal numbers are a subset of denormalized numbers that fill the underflow gap around 0 and floating point. Okay, so any non-zero number with a magnitude smaller than the smallest normal number is subnormal. So would that be a number between the minimum chances? Okay, so can I create this? So we want to use this. Returns true if the number is subnormal. So let's do like 0.001 dot is subnormal. This is an F64. I think it's going to be the exact same. Like, I don't think it matters between F64 and F32, but here we'll turn it into that. This should be false because this is not too small of a number. But if I make this small, enough, I think it'll become a subnormal. It's not small enough yet. I don't know how small it has to be. And I don't know if I'm doing this correct. My understanding of subnormal might be incorrect. Can I not manually create it? Do I have to do math to get it? This is more than 32 digits now in here. Still not subnormal. Do I have to like put in like a 1 in here? And then that will like freak it out? Still false. It's still not subnormal. So I don't know how to like make this. I don't know how to force a subnormal. Can I use min minus like a certain small amount of something? It's like, let's say we have standard F32. Here's our min. So if we just stick with this, here's the smallest number that we can get with an F32, and you should not be subnormal. Okay, false. Now if I subtract like epsilon, probably not min then. Probably like epsilon here. And then I want to subtract standard F32. Kind of like, oh, that'll probably be like 0. Can I divide that in half? And then subtract that. Will this be subnormal? Nope, still not subnormal. I don't know how to force a subnormal. It's not just super small. I guess different architectures have different definitions of that. that fill the underflow gap around 0 in floating point arithmetic. But I don't really know how to get that. Oh, it's based on the mantissa. So we have 6, I think there were 6 digits. So what was that? Like 0 dot, then 1, 1, 2, 3, 4, 5, 6. So if I do that, is that subnormal? Oh, it doesn't know which one to use. It's still false. Okay, so nope. I don't know how to, yeah, I don't, it's interesting, but I don't know if that's really helpful to me. Is normal returns true if the number is neither 0, infinite, subnormal, or nan. Okay. Oh, values between 0 and min are subnormal. So hold on. Min is min positive. Oh, okay. There, that's how we could do it. We use the min positive. So standard F32 min positive. Let's just see what this is to begin with. That's this number right here. Then I want to take you and subtract, essentially. Let's take one tiny little difference off that and see what we get here. It's essentially 0 is what we're getting out here, but maybe are you a subnormal? Are you a subnormal? Which case you're not really 0. Okay, still false. It couldn't actually represent that, possibly. It couldn't represent this. I wonder if I can change more of what this is. But I think it's still turning into 0. Here we go. We finally got a subnormal number. So this one, we subtracted by a small amount. It's basically the minimum positive of like a real number. And I guess real is probably the wrong word. A normal floating point number. And if we take a look at what this is, we can see it represented as an actual number here, but it's subnormal. It's like not properly being calculated by the app. So that's cool, I guess. I guess if it's subnormal, I wonder if math starts getting really weird with it, and it would be better to not use it then. Okay, so is normal to make sure it's not, well, subnormal. Classify returns the floating point category of the number. If only one property is going to be tested, it's generally faster to use the specific predicate instead. Oh, so like normal, infinite. Like what we can get here? We get this FP category, which, okay, so we can get 0. So if it's 0, subnormal, infinite, nan, or normal. Okay, so we can figure out what that is and do basic different math based on that. We can then also do like an if let because this is an enum, it looks like that we're getting back. Is sign positive? Okay, so if it's positive, is sign negative? That's always nice. So you don't have to do like the math. They say like, hey, are if like, you know, greater than 0.0. Takes the reciprocal inverse of a number 1 over x. Okay. It's like if x is 2, so reciprocal minus, okay, so get that. Convert radians to degrees. This is always nice to have when we're starting to work with circles and everything else. Is this 2 degrees? We don't have to do the calculation ourselves, which is nice. And then 2 radians, convert right back. Returns the maximum of 2 numbers. Okay, that's. I mean, it's like nice to have these because we don't have to implement them ourselves. And min too. Now, here's an interesting one. There's a unsafe function toInt unchecked. Rounds towards 0 and converts any primitive integer type, assuming that the value is finite and fits in that type. So what type of int are we getting? Like any type of int? Let's say I do let our number equals like 0.00 like 5.65. Then let I number, so an integer number, it's going to be equal to the number dot toInt unchecked, but you need to be unsafe. And you need a type annotation. Okay, so it can be any type of int. So we can have an I8, I32. So that becomes a 5. As we saw it, like it rounds it down to 0. So it doesn't matter if it's above the halfway point, it goes down. Now, what happens if I go above an I8? So an I8 can be a, let's do like 500. So this should be above. Look at that. We get a -12 because we did interesting. Okay, so we did a -12. Did it wrap around? What's the maximum I8? Let's just double check that really quickly. So debug standard I8 max. It's not 255, it's something slightly below that, right? 127 is 255 essentially divided in half. So is 128 going to be -127? -128. Okay, so we have -128 through 127 is our choice here. So it wraps around. It's a circle. It wraps around as we do this toInt unchecked. Now this reminds me a lot of what like the old games do, right? Like the really old games they have in like cartridges or from like the 80s or so, where it's basically just, okay, we just buffer overflow and it just wraps around to the beginning again and you start getting new things. And if you do that, you can get some really interesting results, usually for like speed runs or other things. I don't know if I'd ever want to do something like that here, but what is fascinating is that I can't actually get a failure. Now, what happens if I try to not do the unsafe conversion? What if I try to convert this to an i8? So let's do another debug here. I'll take my number as an i8. What happens here? You just become the maximum number you can be. It doesn't wrap around. You just become the max. And it's probably going to do the exact same thing for all the other I's or the U's. Can I turn this into like a U8? Yeah, this works at U8. So if I go into like 258, it should give me 2 because it wraps around back to 0 and then starting up again because there's no negative use. Okay, so that's good to know. So that's interesting. I didn't expect to see any safety, like unsafe things happening here. The value must not be nan, not be infinite, be representable in the return type int. Okay, so if we did this, divided by 0.0, which I think makes you infinity, this is gonna be a problem. You just become 0. Yeah, you're infinity, but this I number that we just got is a 0. So it actually kind of works, but it becomes like in a 0 right in the middle. And then not a number is like 0 divided. Yes, I know. Clippy, let me do it. Again, it becomes 0, but we have not a number here. So no matter what, we're going to get a 0. And even though it says you must not, it must not be non or must not be infinite, we don't get like any kind of like crash or any kind of like memory corruption type stuff. It just becomes a 0, which is not bad. Okay, so we have 2 bits, raw transmutation to U32, which gives us the... What kind of bits are those? Binary? So... So that's the decimal representation of the binary representation of 155, I think. Can I tell you? I think debug now has the ability to do something like this, right? Where I can say, give me, oh, what's the binary? Oh, I forget how to do that. You have to do this in print line. It's not B. Oh, I forget how to do the. Forget how to do that. Restlang print line. Okay. Oh, it is. It is that. Oh, hash B maybe. Oh, I have to format it? So format you. With binary. And then we'll put you in here for the print line. Did I forget the quotes initially? That might have been the problem. Okay, so that gives us this. So our 155.5 is this in bytes, in bits. Okay. That's interesting to see. So I wonder which one is the decimal point showing like where the decimal point is. Like 5 is like 4 and 1. I don't know where exactly that would be. That's not 5. That would be 6. 1, 2, yeah. And this might be wrong to like convert it over to bits and then convert it to binary too. Two bits is not casting. It's actually giving me the bits. Oh, it's a transmute behind the scene. Oh, it's essentially identical to a transmute. It's distinct from as casting, which attempts to preserve the numerical value and not the bitwise value. Okay. And then we can do from bits to get that back. Floats and ints have the same endianness on all supported platforms. Oh, so if I need to preserve if I need to transform to an I, but preserve some things, can I do from bits? Okay, so there's going to be the byte that represents nan. There's going to be the byte that represents probably infinite. There's going to be the byte that represents the decimal point, like where things go left and right, I'm guessing. To B bytes. Return the memory representation of this floating point number as a byte array in a big endian network byte order. Oh, interesting. Oh, to Ellie? Oh, because it's big. So the B is big endian versus little endian. And native byte. Native endian? Okay, yeah. Native endian. I don't know when I would want to use that. It's interesting that it's here. And that we can look at it. Clamp is always nice. The ability to say like, hey, make sure you're between these two values before we then do something else to you. And then we have our trait implementations, which is all the good stuff. Okay, so I think that's it for F32. Yes. So that's it for all the, like, essentially all the floats I think are the same, right? Now, I don't mean like they actually are the same, but I think they have the same methods, right? So if I look at like F64. Here, if we go back to standard, they should have primitive types. So we have F32, F64. That's it. There is no like smaller, there's no like F8. That's it. So I think F64 has, I think, the same stuff on it. Yeah, I remember the copy sign. All these fun things. I think everything you can do with F32s, you can also do with F64s. Yeah, okay. I'm seeing exactly the same methods on here. Yeah, and that makes a lot of sense. Basically, it's just how much memory is taken up by the number and how small of a number you can get. So like the constants are going to be different, but the general math is going to be the same. So essentially, that's like our F32 and F64 all together taken care of. So like you're pretty much the same as the F32. But more memory. Now, looking at what's coming up next, function. This could be a lot of fun to go into. Oh, there's gonna be a lot here. This might be the rest of our day. Talking about the rest of our day, I need to go get my I need to go get more water. So I will be right back, and then we're gonna take a look at function, or function pointers. I guess the primitive type function. That's gonna be fun. So with that, quick break. I'm back. All right, so I've been looking forward to functions, learning like specifically the primitive type function for a while because, we went through the book, and it talks about the function type, fn, fn mut, fn once, and then sort of like passing them around and using them, but I never really got too deep into it. I think we're gonna change that today. So specifically for function type pointers. So it is an actual type. So I think what this means is that we can create an actual variable which holds a function, which I think we can see, because I think we can pass that in as a variable, right? So let's come back into here and reset this a little bit. Not using you right now. Okay, so if I wanted to store a function into a variable, and it's really just a type, I think we can do that as a normal function or as a closure. And I know closure is not the same as a function, but they're close, right? So can I say something like let a equals let's do like a closure that takes x and we just return x plus 1. So that's that. But I don't think I can do like the JavaScript style where I can do like let b equals function like function x plus 1. Like that's not going to work here. But I can create a function down here that does that. So a function like add 1. We're going to take an x, which is let's just say an int. And we're going to return a i32. We're just going to say x plus 1 for that. And I should be able to now do let b equals add 1. Like that. So now I'm storing the function itself. Notice I didn't call it with the parentheses into here. So now we can later on do like debug of b5. And this should work. We should get 6 out of there. Oh, you're upset because you don't know what those are. That's fine. And this works. Like totally possible to store a reference to a function inside of add 1. Or I guess as a pointer to a function. Okay, so function pointers are pointers that point to code, not data. They can be called just like functions, like references. Function pointers are, among other things, assumed to not be null. Right, because they're actually code, right? Like it's going to be static. It's in the binary. So if you want to pass a function pointer over FFI and be able to accommodate null pointers, make your type option function with your required signature. I guess like if I might not have a function. Oh, I feel like I'm assigning to it in like an if statement, maybe? Safety. Plain function pointers are obtained by casting either plain functions or closures that don't capture an environment. Okay, so like it's just completely captured in. Okay, so we have this function add one. It's literally what we just did. And that's a function usize in here. Interesting that we're using these parentheses to denote the type. I guess that makes sense. Whereas here, a closure, okay, so same idea. And it's the same type. And we can use it in the same way. In addition to varying based on their signature, function pointers come in two flavors, safe and unsafe. Plain function pointers can only point to safe functions, while unsafe function pointers can point to safe or unsafe functions. So, we can do our new cast to I trick here. So let's do we have an unsafe cast to I, which is going to take an F32. So we're going to have our number, which is an F32, and we want to return an I32. And the way we're going to do that is we're going to say our number dot I, what was it? Number dot oh, come on. We were just looking at it. To int unchecked. Okay. So we do that, and if I want to store this away, how am I going to do that? So here's our unsafe function. So our unsafe pointer is, oh, we just have it be unsafe here for the type. Interesting. So if I just have you be let cast to I equals, or I guess like unsafely cast to I equals cast to I, like that. Rust Analyzer seems to not be telling me what this is. I mean, that's maybe not surprising. Let's try restarting and see if it gives me my types again. No, it still doesn't let me do that. But I should be able to now debug. I don't think I can safely call this, right? Because it's unsafe. So like I would have to, in an unsafe block, call it. Is that? So I guess we're just saying that this is, if we put the unsafe keyword in the type here. So this is an unsafe function that takes in the F32 and it returns an I32. Then when I try to use this, it's going to yell at me. So if we try to unsafely cast I, like a 10.0, you're going to yell at me because you need to be unsafe. Oh, that's why I missed the FN. Yeah, okay, so call to unsafe function, we have to now wrap this debug in unsafe. And then we can do this. And then it works out for us. Okay, so our other one, if we put this back in, we have this, so like safely cast to I, taking our number, which is an F32, I32, and we do an as, so it is safe. I'm just going to store the function in here, and we can see, okay, your function safely casts I, you store an F32, and then you return an I32. Okay. So can I'm going to override this to make it unsafe function. This is going to be an F32, I32, but you're holding this safely cast I here. Can I use this without the unsafe? So debug safely cast I. Or is it going to make me put this in the unsafe block? No, that works just fine. Oh, and I need to like actually call it. No, I have to throw this. Okay, so by telling it, hey, you might hold an unsafe function. It's possible to hold an unsafe function in here. Now when I try to use this, even if it's a safe function, I now need to wrap it in unsafe. Here. Which is, I guess, interesting, but because yeah, so you're really unsafe as a pointer, but we still have to now wrap you on an unsafe. On top of that, function pointers can vary based on what ABI they use. This is achieved by adding the extern keyword before the type followed by the ABI in question. The default ABI is Rust. Okay, so as in function is the exact same type as extern Rust function, a pointer to a function within C ABI would have type extern C function. Can I do that myself without having to bring in like FFI C? So extern ABI blocks declare functions with ABI. The default here is C. Functions declare an extern block as C ABI. Okay, so supported ABIs. So there's a bunch here. Interesting. I wonder like what, like fast call. I wonder if that's like actually literally faster. Are there actual like explanations on one of these, on some of these? No. And if I just try to write like the C myself. So how does this work? We're going to be doing, so extern ABI and then have a block. So we're going to do function C add 1. And we're going to take in a number, which is a, let's just say F32. return an F32. Here, we'll do U32. Make it easier. Now, if I do an extern C and then block, but then I just say number +1, and we're turning out of here, it seems to accept that. So let now would I normally put the function inside of here? Probably not. Now can I call this? Like let C add 1 equals C add 1. Doesn't show if it's any different. And if I try to run this, do you have to be an actual quote? I wonder if this has to be quotes. Interesting. Okay, so extern C, I think I have to write actual C code in here. So expected one of bang or : : oh, I kind of forgot how to write a function in C. Let's try extern C block here. I don't think I have to put like a header file type thing. I think it's like a function. Is it full function like that? C function. Oh, we have to give the return type function. Oh wait, there's no function keyword. Oh, I totally forgot that. That's how it is. It's really old school. Okay, so U32 C add 1. Is it the type first? It is the type first. So U32 number I guess like in good old C, you usually do the one true bracket style, and then we're going to return number +1. Now this C add 1, I want to, is everything else going to work just the way we expect it to? No. Expect one to bang or : : extern C function blah. Yeah, that's kind of what we're going for. Oh, that's what we have to do. Okay, so it's not this. Extern C then function blah. Okay. So extern C function C add 1 takes in. Oh, you know what? Oh wait, no, that's fine. I mean, you're not yelling at me, which is something. Well, actually, you are yelling at me. Expected 2 arguments. Why? Wait, what? Oh. Oh, okay. So I have to write it as a, okay, so this doesn't let me magically write C. It's still Rust syntax. Okay. I was wondering whether or not I was just like, okay, I magically write C now. It's a sort of like, okay, that's what we're doing, but it's not. So if we run this, okay, so it runs correctly. Now, is this actually using C to compile it? And it's certainly not unsafe. Also, we can try this extern block again. So if I want to do extern C and then have this block here. Okay. Incorrect function inside extern block. You might have meant to write a function accessible through FFI. Oh, okay. So that's not it. Extern blocks define existing foreign functions, and functions inside of them cannot have a body. Okay. So, what's a C function that I have access to? Like I can do this, right? But of course, this function doesn't really exist in C. What's I think, do I have C, I do have GCC here. So can I create a library and then insert it? I don't remember if I can do that. So like, can I, you should look at it as extern C defining an attribute on your Rust functions. Okay, so extern C, and then pulling this. Okay, so defining an attribute on C add 1, which is exactly the same as if I just did extern C function add C. Okay. Is there? What's a library? What's a C library thing that I can pull in? Form an FFI. Like standard lib C. Because is there we have like string to integer. Okay, we could just try this int rand. I don't want to do anything else really. We can get the absolute value of an integer. Maybe this could be better. So absolute value of an integer, but then we have to, okay, so we have to pull in and use. I think we have to use C, or like there's the FFI. I don't remember. I don't think I can just say, ABS int, right? Your I32s. Then if I pull you in, now we have this ABS. So I want to I guess this is going to be let C ABS is going to be equal to ABS. Operation is unsafe because it's coming from C. Okay, so that's good. Like we finally got it so that it's recognizing that it's an FFI interface for C. And if I do that 5, will it work? It does work. Okay, so if I do -5 and we run you again, we should get 5. And we do. Okay, so that's as simple as it is to essentially declare a function from C. So as long as you know functions from the standard library from C, you can grab them in with this extern C like that. We can do extern C function or in a block like this, and then just use them. And then we just say what it is that we're getting. And we can associate it, we can throw it into a variable like this, or we can just call it. Either way, it will require unsafe when we call it. That's actually kind of nice. Let's see. Variadic functions. Extern function declaration with the C or CDECL ABIs can be variadic, allowing them to be called with a variable number of arguments. Right, because C and some other languages allow that. Normal Rust functions, even those with an external ABI, cannot be variadic. For more information, see the, okay. So interesting. In Rust, we can't have like a variable number of incoming arguments, but in C you can. Creating function pointers. When bar is the name of a function, then the expression bar is not a function pointer. Rather, it denotes a value of an unnameable type that uniquely identifies the function bar. Okay, so this is not a function pointer. Unnameable types. Remember that if you want to expose your Rust functions to be accessible from C, you need to add no mangle to them, since Rust mangles names by default. Oh, I didn't realize. I guess in a binary, I get when it compiles. That makes a lot of sense. So we have to, okay. And I'm not going backwards in this case. We're just calling C from Rust, because like there sometimes are things to like grab random numbers. Like for example, there was that entire rand, right? Like we saw in here, there's a rand which will give us a pseudo random number. And we can even set the seeds and do all that kind of fun stuff. But we can look at that later. So, okay, the value is zero size because the type already identifies the function. This is advantage that calling the value, it implements the function star trait, does not require dynamic dispatch. This zero size type coerces to a regular function pointer. At runtime, I assume? Or at compile time? So it's also zero sized. Okay, so it takes up zero size and probably doesn't add anything to the runtime either. Oh. But if I add this, force coercion to function pointer. Does that take up space? Okay. That doesn't really show. Oh, okay. The zero size type coerces to regular function pointer. Okay, so we can coerce it, but it's still, so this is a pointer. So hold on. I'm incorrect. These are function pointers because we manually set the types. And I think, can I just do that? No. Oh, because, okay. These are function pointers. We manually set the types. This, however, is not, right? This is a zero sized unnameable type. So type representing the function. It could be coerced if we want to. Now we have this reference here too. It's a shared reference to the zero size type identifying bar. Okay, so here, let's grab in rand. So there's rand, which takes in absolutely nothing and returns an i32. So then we'll have, this is a reference to a zero sized unnameable type. And you're going to be a reference to rand. And so we can then call you here and unsafe. There's our random number that we created. It's truly random. Wow, truly is maybe strong. It's pseudolly random. Okay. So a reference to bar is basically never what you want when bar is a function. Okay, that's interesting. So even though we can use it as this, we never really want this. So don't do it. Okay, function pointers implement the following traits. Clone, partial, equal. Oh, so we can check to see if the functions are equal to each other. Interesting. Now the Rust, sorry, the C API for Rand, does it allow me? Okay, so we can do another one here. So function Rand. I want you. I guess I can't. We have to do like a Rand i32. No, I can't do that because that's not the name of it. So I can't do it twice. But I can grab these. I can grab it twice, right? So I can do Rand equals that. Let other Rand equals just Rand like that. I don't need unsafe right to do a debug compare, right? So we can do Rand destructured Rand is equal to other Rand. Interesting. So I can't actually do it even when I'm trying to destructure. Oh, I think I have to do that. Oh, it doesn't let me do that. Can I alias it? We can alias this side. So they're both showing reference. Oh. Interesting. Oh, crap. Because I call this Rand here. This is Rand i32. Hold on. That's why. i32. This is going to be Rand i32. That was my problem here. So if I do that and then dereference you, cannot be applied to type unsafe extern C. Okay, so it can't. So partial equal, it can't do that. As Dallin, AZ Dallin, AZD Allen. Hello. What do you mean by alias it? I don't know if I'm familiar with aliasing. Or is that just like then setting the type directly? Now, if I do this as like not a reference, but the same, I still can't check to see if they're equal to each other. Now that's like the actual C functions. So what if I did this to here, safely cast to I. Okay, so that works. So it's the unsafe ones. It's the unsafe CFFI function that doesn't let me do that. You wonder if external calls in Rust that you could give it figure types out and you just give it a wrapper or alias that you can name whatever you want. Oh, like a CLI alias. That could be interesting. Yeah, because this is Rand with an i32, but if I wanted to like have a different i30, like an i64 or an F32 here, how would I do that? Yeah, That is an interesting thing. I don't know. We haven't looked at FFI stuff very much. So and I don't think I can do this again. I could make this maybe like T. And now if I do that, I have to extern T. All right, no, not there. At the function level. Not there at here level. Foreign items may not have type parameters. Replace the, oh, okay, with concrete type. So I can't do generics with the FFI types. I have to do something like with the U32 or an F32. You know, that's a good question. Let's find out. So if I do F function rand, we got two of these. We have an F32 and we have a U32. The name rand is defined multiple times. Rand must be defined only once in the value namespace of this module. Can I do another extern C? Oh. I think I would have to do a wrapper. I think I'd have to have different files and different modules, and then I can do that and wrap around it, I bet. Exactly, an F32 module and a U32 module. I bet that's exactly how to do it. And now doing this, everything else will sort of work. You're so upset, but that's okay. So if I run you, everything is now good. Although notice that this rand, ignore the fact that I have it called rand I32 because it doesn't really care. It doesn't give me F like a floating point number just because I asked it to give me a floating point number. It gives me an integer because that is what the C programming library's rand gives me. Just an integer. I don't think there's one that gives me a float. But interesting. So if there is a function which is insanely fast in C compared to Rust for some reason, we could very easily pull that in and just start using that in our code. And we can wrap around it on modules so that when the Rust one becomes faster, we just switch around to using that one instead, which is nice. Okay. So Rust functions implement partial equal and equal. So let's do it up here. Let's see. Yeah, Rust is quite good at FFI. It's almost a shame not to use it more. I know, I'm just like not familiar with the C standard library. So like it's not something I like immediately go to pull out, but the fact that it has it and it's so friggin' easy, maybe we should like look into that a little bit more. Darth Millennial, hello. In addition, function pointers of any signature, ABI, or safety are copied. And all safe function pointers implement fn, fnmute, and fn1s. This works because these traits are specially known to the compiler. Okay, so we can copy, I can copy rand. So like this other rand, let's do this. Let's rename you to be what? Let's put you back to an I-32, because that's kind of what you are. And let's now say that this is other rand equals rand I-32 dot. So if I do this, it's been copied. So other rand today we are diving deep into the Rust standard library. So we looked at the floating point numbers a little bit earlier today, and now we're looking at functions. Now everything else implements fn, fnmute, and fn1s. All safe function. Okay, so unsafe doesn't implement those. Safe implements. So fn, fnmute, and fn1s, because it is a Rust function and safe. And then, okay, so then we have our trait implementation. So that's it. Like just tons of these trait implementations. Oh, look at this. Look at all of these like impulse for extern C. Wait. I could implement on extern C stuff? Wait. Can I actually do that? Can I impl? What would I want to impl? I don't know if I want to do like a debug. We can do a debug. So if I do, let's first try debugging other rand. So debug other rand like that. Okay, so unsafe extern C doesn't implement standard format debug. Okay, so let's see if we can do that. So impl, what is it? Standard format debug for unsafe extern C rand. Oh, it would be this function like that. Function like that. That returns an I-32. Okay, so I want to return this formatter. So we're going to return f dot, I think it's right. Wait, what was it? It was like F. Oh, I completely for. Oh, is it right like that? It's right F. Okay, and then whatever I want to put out here. So you called a random number and we return you. Conflicting implementations of trait standard format debug for type unsafe external. Oh, okay. So at 32, only trace to. Oh, okay. So it did implement this. So, cannot import this ourselves because the standard lib already does it for us. But I can't actually call it as if it does because there's no unsafe extern C function at I32. Oh, that's too bad. I kind of was hoping that it did implement that. But it both does and doesn't? So functions are interesting in that way. I sort of was expecting this to be a lot longer, but there's just a ton of these trait implementations here. So yeah, I guess that's it. So let's see. Okay, what do we got here? You don't like this because deny Clippy. Okay, so we're going to allow everything. We're going to allow you to do this. Wait, I need to say allow. Unused variable other rand. Okay, so let's also allow dead code. Oh, it's unused variables. That's what it is. Okay, there we go. No more errors. I'm gonna copy you, come over here, and we're just gonna say functions are fun. So functions and splits. All right, well, that was vastly overestimated the time it was going to take us to go through that. I just saw the size of that file and was like, oh, it's going to be a lot. We have the integer numbers. I don't know how much those are going to be different from each other. We could take a look at them. Because I think all the numbers are very similar to each other, just with the size they take up in memory, I believe. So let's go to I32s. And we're going to skip over everything that's nightly only. So I guess let's also double check that the assumptions. I'm gonna go open you up again and go to I64. Heck, let's go to the max, I128. Is there an I256? I don't think so, right? No, that's only use. Well, right now I can tell a difference. There's going to be, there's some nightly only stuff on I32s that are not on I128s. We can see here, like widening mole is not on here. So we have min. Interesting. Okay, so starting here with min. So min max bits. Min max bits. Oh, okay. I bet from now on it's exactly the same. Returns the number of ones in the binary representation of self. That's... You only consider Rust because it can work exactly at the same level as C. That makes a lot of sense. And it does it really well. It's basically like once you do that external crate, yeah, you're gonna have a lot of unsafe blocks, but as like that's the only difference really, right? Like you're just saying unsafe and then calling C things, and as far as you're concerned, it's just Rust. Okay, so these all, okay. I think the rest of them are the same. It's hard to believe though, because like it's over one page. It's gonna be interesting. All right, but let's see. So we have our standard. We have our min and max. Like the maximum, the minimum that it can be, the maximum that it can be, the size of this integer type in bits. So not the value, but the size of the integer type in bits. It was a smart move to make sure people could create bindings and start using Rust incrementally. I mean, I don't think they did it for us. Like from what I understand, the history of Rust is that Mozilla was using it as an internal tool to like slowly rebuild Firefox into Rust. And so they're like, well, let's design a language that allows us to slowly move things from C and C++ over into Rust. And so the way they did it made sense completely for themselves and just happens to be really good for everyone else too. And I guess that's gonna be another interesting thing is like, how do you pull in external like C libraries, like your C functions that you have? Is that just a use statement? Like you use the file and you just pull that file in? Because that makes it even easier. I programmed Rust C so long ago that I don't have anything on any public source repositories. I don't even know where that code is anymore. I bet it's all gone. Let's see. So from string radix converts a string slice even in a given base to an integer. The string is expected to be an optional plus or minus sign followed by digits. Leading and trailing white space represents an error. digits are a subset of these characters depending upon radix. What? So I want to check this out. From string radix sounds interesting. So this is primitive integers. Okay, so there's this from string radix. We can give it a source, and it's going to give us an I32, but it's a string slice. So I would assume that it wants us just like a single character or a single thing. So let's say we have a let our string is going to be equal to, okay, so we'll have a string slice of like hello world. Now if I debug just like a little tiny bit of that, right? So string, can I do something like that? No, I can't do that. String indices are ranges of usize. Wait, do I have to give it a usize? Can I actually? Oh, can infer type. Okay, so let's do usize. Oh, okay. I was kind of expecting that to work because, hey, string indices are ranges of usize, but I need to give a range, I think. So a range would be something like, what is it, like 0.1? Doesn't have a size known at compile time. Do I have to do this for an actual string? So like, if I do, that's toOwned to make this an actual string. Let's give a string slice, which I might be able to. I can't debug this there. Let's see. I don't think I can do something like this now, right? No, okay. So and it won't figure out what it needs to be. I can like do as chars, but I don't want to do that. I want to do as slices. It's like slice equals, I already forgot how to do this. It's like string, if I do like 0 dot, let's try print line. Instead of debug. Are you more happy? No, okay, I don't know this string. Oh, we need to borrow. We need to borrow. Okay, there we go. Now I get our H. Okay, so I get the H here from the slice. Was I not borrowing it before? Is that the reason why it didn't work? Can I do a debug now? Yes, I can. Okay. Why do you run twice? Oh, okay. That's what I need to do. Okay, so we have our string slice. Now what I want to do is take this string slice and we're gonna run this from the string radix, which is off of eyes. So okay, so let rad, I don't know what this is. Here, we'll do standard I32 dot from string it doesn't have a self on it. So standard I32 from string radix. The source stir, so the slice, and then the radix, which is a U32. So let's do, I don't know, like 15. You just ordered a pizza. Nice. Okay, so it's not found in standard I32. We are in I32. I don't see a self on this. Okay, let's take a look at our examples. Wait. I accidentally closed it. Yeah, okay, I32 from stir radix. Okay. So standard I32 from stir radix. Am I not pulling it in from the wrong place, the right place? Like here's this standard I32 from stir radix. We give it the slice, which is a reference to a stir, and a radix, whatever, we don't know what that needs to be. Okay. This panics if radix is not in the range from 2 to 36. Okay. Why don't you work? Not found in standard I32. Can I just do this on I32 like that? I can. Okay. Invalid digit. Okay, so like so we know, let's do this debug again on the slice. We know our slice is this H. Invalid digit. I guess you're turning it in. I want it to be this H here. Interesting. So it's, if it's that A, if it's capital A, it's a 16. So let's do that. Bring in a 16 here. Okay, so you're an okay with a 10 inside. Is that, so A becomes a 10. That's not oh, what is it called? The HTML, the ASCII code, right? No, I don't need your cookies. Okay, so I want A. Here's this capital A. Your ASCII code is 65. That's nowhere near 10. So, okay, it has nothing to do with that. I guess is radix? What's a radix then? The radix or base is the unique. Oh, right. We looked at this before. It's the unique number of digits, including the zero, the digital zero used to represent numbers. Oh, so like, okay. If I want base 10, so I want you to be 10. Invalid digit. Base 2. Will you be binary then? An invalid digit. Base 16. Gives us this 10. If we look at, is there a hex in here? No. I almost wonder, we got binary. I guess we're not gonna find it from this table at least. But I don't really know what radix I would need to choose from to get the number out of it that I'm expecting. So converts a string slice in a given base to an integer. And it's going to panic even though it returns a result. That's interesting. Okay. I guess we're converting, but there's other ways to convert, right? Like I can convert an actual just string slice, right? I can just do debug slice as I32. I think that's something I can do too. Cast through a raw pointer first. Oh, a raw pointer. Ooh. I don't have that. We would need to create a raw pointer, which we don't have right now. We could do that. Or I have to turn into a character. Oh, maybe chars do that. Can I get a raw pointer here? I can do as ref. I can do as pointer. Do chars. Yeah, I know. I've got I need to like position the camera slightly better, but I don't have like a system for that yet. So I'm now tiny. Also, hello according to Bo. So let's do cares the first, and then see, can I convert that? Okay, so it doesn't like that, even if I'm trying to. I wonder, can I just do like literally do that? No. Okay, so I can't convert it. I think I can convert it to a U32, but not an I32. Oh, not is it U size? There's a way to do that. I need to cast your raw pointer. So we've done raw pointers before. What was how did we get it? We got we had to create the memory location and get that, then we can get the raw pointer. We could do that, but that's sort of like besides the point with like what we're trying to dive into, which is integers. So the from string radix is interesting. Like we're converting this slice into like base 16, but is that like is that like a 65 in base 16? Because we're gonna need a 10. So 10 base 16 to base 10. Oh, I was kind of hoping that it would just tell me here. What's the symbol for base 16? I don't remember how to do that. So 10 in base 16. Oh, 10 in base 16 to base 10. Okay, so okay. Hex base 16A is 10. So that makes sense. That's what we're seeing here. We're seeing the hex, the base 16 of A is decimal 10. That's what we're getting. When we do this. So looking at this, we should see B would be 11 and so on and so forth. And we can do, I guess if I do binary to decimal, if we do like A, oh, that doesn't work. Okay, so that's 10. If I do lowercase a, oh, that doesn't like that at all. Okay. There's no A binary. I guess it would just be 1 and 2, right? So can't really do decimal for that either. It's got to be. Huh. Oh, decimal doesn't make sense. Yeah, I don't know how to do the radix for other things to make it more interesting. like 32. Like if I say, hey, give me that, I don't think it will. It's still 10, even on base 32. I guess that makes sense. It'd have to be lower than 16, like 15, base 15. And we're gonna get a different number, or, oh no, it's still 10. Oh, I have to find out what, okay, it has to be lower than base 10. It has to be lower than base 10. So if I do base 10, it's still gonna be base 10. So if I do base 9, is that out of invalid digit because it's not large enough to hold the 10. I think that's what it is. It needs to be large enough to hold this. So either way, don't need to worry about it too much. If I do this lowercase h and we go all the way to 32. There we go, 17. We just have to make sure it's large enough. Okay, so count ones, count the number ones in a binary representation of self, which is interesting, but I don't. So when we did the ECS stuff, we compare the ones like that are even to each other, but we don't necessarily compare just the number of ones. We don't really care about that. I guess we can count ones to see, oh, the number of components that it has. That could be interesting. That would be count ones would be that. And then count zeros would be the number of components it doesn't have. That doesn't make sense. Leading zeros, return the number of leading zeros in a binary representation of self. Okay, so I don't know when I would want to use those. Trailing zeros. Leading ones, trailing ones. Okay, rotate left. Shift the bits to the left by a specific amount, wrapping the truncated bits to the end of the resulting integer. Oh, wrapping. Okay, so if it's all the way to the left. So let's say we have like we were doing this with like a map, right? So let map equals 0b. Let's do this with like a 8-bit, even though we're working with 32-bit here. 1, 2, 3, 4, 5, 6, 7, 8. So if we start here. And so that's going to be what? 1, 2, 4, 8, 16, 32, 64. So that should be 64. Let's make sure I'm correct on this. With the next one being 128. Okay, so there's our 64, and then I want to rotate left. Rotate left by the amount. So the number, I'm gonna rotate left once. And that should give me 128. And map is not mutatable, so it's immutable. So I'm not changing map, I'm just creating another number here. Error. What's my error? I must specify a type. Oh, because it doesn't know if it's on an I-128, an I-32, an I-8. So, okay, we have to give you an I-32 here. and then this should work. There we go. Okay, now here's our I-128. Right, because it doesn't know when to truncate and like remove it down to the left-hand side, right? Because if it's an I-128, we got a lot more room because we got 128 of these. So now if I keep on going to the left, we have, let's actually switch this to an I-8. That will make it a lot easier for us. So we're at the 128, which is the max of an I. And then if we do it one more time, it should become a 1. A negative 128. Hold on. Did I do this right? Well, wrong. Let's do debug just the map to begin. $64 and then negative 128. Oh, because this one, oh, is that the negative? Is that showing what the negative value is going to be? Out of range. 1, 2, 3, 4, 5, 6, 7, 8. So it's I-8, but I guess I can't do one more of it. Is it only 7 that's allowed? Because the 8th one is used for the sign and the negative? That's probably what it is. So I have to remove one of you. You become a 64. So seven ones in a row is all we can have with an I-8. With the final hidden one here being a negative. Being the sign, really, that makes it negative or not. Now it rotates over, but instead of coming here, it goes to negative 128, which would be everything 1, right? So 1, 2, 3, 4, 5, 6, 7, 8. Then you're going to show as the initial map your 127 and then negative 2, negative 2. Okay, this is not happening the way I was expecting it to. Okay, so rotate left. What exactly are you doing? Shift the bits to the left by a specific amount. Okay, so I was kind of expecting that this was the same as that, and I didn't read the next line. It's not the same operation as this bit shifting operator. Shift the bits to the left by a specified amount. So what's going on here? Well, that's not. What? Wrapping the truncated bits to the end of the resulting integer. I guess. So if I take the bits of this I-8, so we get 7 of them. 1, 2, 3, 4, 5, 6, 7. So if I replace you, and we're going to do a rotate left. I guess those are always the same, right? So I rotate left like that. So we start with 1 and then we get 2, which 2 would make sense. But also that's the same as a bitwise less than operation. but specifically this is not. Now, like normally with rotate in like a matrix, it makes sense. You're doing something like that, and you're rotating like the X to become the Y's and the Y's to become the X axis. This, like, I guess I'm having trouble sort of like imagining what this looks like and what's actually happening behind the scenes. Is there like a Wikipedia article on this? Like integer rotate left? Explained? Integer rotate left method is used to shift the bits of an internal integer value represented as binary 2's complementary form towards left by a specified number of bits. Bits are shifted to the left or higher order. Okay, that bit rotation. So a rotation or circular shift is an operation similar to shift, except that the bits that fall off at one end are put back onto the other end. In left rotation, the bits that fall off at the left end are put back on the right. In right rotation, the bits that fall off at the right end are put back at the left end. So let n is stored as 8 bits. Okay, so if we have this like 111-00101 by 3 makes it, it's like this. So 1, 2, 3. So 0, 0, 1, 0, and then all the other ones, okay? But I can only create, because an I is, we get 7 bits, but the 8th bit is the sign. So I can't define this as like 8 bits here. I can define this as like, I can define this as this, right? So I have 1, 2, 3, then this. So this is 1, 2, 4, 8. So 8 plus 4 is 12. Plus 2 is 14, 15. Is that right? That's 15. And then I'm going to rotate this left, and so that should be, this should be a 0. So here, I expect this to now be 0, B, 1, 2, 1, 2, 3, 4, 0. I expect it to be that. It is, okay. So that's what happened. Now, how do I want to do this? Oh, come on. Okay, fine. 0, B, 1, 2, 3, 4, 5, 6, 7. So now, so if I do this, what we're gonna happen here when we rotate this left by 1, you go off to the end, right? So you're gone. But instead of being placed here, it gets placed in the sign location. which is makes it a negative number. And then this is so 1, 2, 4, 8, 16, 32, 64. 64 plus 32 is 96. So this would be a negative 96 and a positive 64, 96 plus 16. 96 plus 16 is 1. Oh, now it's over 100. Like 104 or something like that. Around there. 112. But interesting, so we see this as a 96. This is a negative 32. Shifting and rotating is traditionally avoided on signed integers. I could imagine why. Like, look at this. This is like, I can't predict what this is. This is a negative 32. But I'm not allowed to set the sign when I'm creating it through binary, which is like making it really hard for me to predict what's going on when I'm like looking at this. Like, okay, 32 is, so 1, 2, 4, 8, 16, 32 is just that, So I rotated left by 1, but I lost 2 numbers. What? Okay. Apparently I don't know any of how this works. Now, if I did this on a U8, is this gonna make more sense? So in this case, I shift over by 1, and I should have you turn it into a 0 and you turn it into a 1, right? No. Okay. So it doesn't even happen the same on U8s. (128 minus 32 is 96. Right, okay. I guess I still don't understand the rotating left. I thought it was rotating by like moving everything over by a certain amount. But then when I try to predict, because it's coming on to the right hand side, but that doesn't seem to be what it's doing. This is, we're getting 97 here. After the rotate left, we're getting 224. Hold on, can I, we can do, give me binary and give me binary. Okay, so after the rotate left happens, oh, I forgot. I have the wrong number here. Okay, so we have 2. Okay, this makes sense now. The U's make sense. When I'm rotating left, it's like this falls off the end and it comes over here. And so we see that happen right here. The I's don't make as much sense to me. So if I do the exact same thing as an I, we have to remove one of the zeros for the sign. You move, okay, you move one to the left that we see here. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that one becomes the sign, right? Planet was taking, hello. Rust is hard, you can't learn. Rust is, well, I guess it almost depends, right? Like how it can definitely be hard. But it can also be like, it's one of those things where it's like, it depends what you're doing. Because like there's some things that are incredibly hard, and there's some things that are like not quite as hard as like, you know, other languages trying to learn. So I guess what's super hard about it for you? Or what are you trying to do where it's super hard? So there's our sign. So you're becoming that. The syntax. What are you coming from? Like what's your history with programming languages? Because if you're like there's some programming languages syntax that are similar to Rust, and it'll probably be easier coming from them. Coming from something like, I don't know, let me think about like what, like maybe Python might be a lot more difficult. JavaScript could be a little bit weird because you're never using like types. So if I can't set this myself, and we have so what would it be? It would be 0, 1, 2, 3, 4, 5, 6. Great Jack, hello. You love Rust syntax, but you used it over 4 years. Yeah, it's something like once you get used to it, obviously it's like ingrained and it gets internalized. It's a lot easier and it makes sense. C#, Lua, TypeScript, PHP, C++, technically assembly. Oh, okay. Yeah, like that's a good assortment of different sort of like syntaxes to come from. And yeah, I haven't done C++ myself, although I've done Lua, TypeScript, PHP, JavaScript, done those. I didn't do C#. It did, I guess like the borrow checker was like the thing that hit me the most when I first started. Oh, and Java. Well, do people really admit Java these days? No, I'm just joking. Yeah, totally get it. Like it takes a little while. It is pretty different. It actually reminds me a lot of, like, there's some things that remind me of JavaScript. There's some things that remind me of like even just doing like the weird Lua stuff and like tables. But yeah, it's sort of like a hodgepodge of different syntaxes thrown together. This thing. So this is a so like think of it, I think in Python it's like a range, but here it's this sort of is like a range thing, right? So I'm basically saying for this string that I have, this type string, give me a slice that's between position 0 and position 1. So give me the first character is what's happening here. I can say, now where it gets really weird is if I don't put on the final letter, it's just saying, okay, give me everything starting at position 0 through the end, and don't worry about the end, just go until the end. Or I can say, give me everything from the beginning to position 5. All of that works and is completely legal. And like that kind of stuff, I think is really hard to like, if you're not used to that and you haven't seen that in another language, you're not going to get that right away. It's going to take a while. For you, what personally makes you harder to get into language is a type system. You use so many different syntaxes, you don't care much about it. I hear you. Like after using Rust for a while, now every type system feels less strong than Rust. And I just want Rust. If I'm going to have a strong type system. Like, ironically, my desire to use TypeScript has gone down since I've learned Rust, because if I'm not going to have as strong a type system, I almost might as well just go free. On the Restbook thing, you don't want to read the entire page about how they implemented memory stuff. Yeah, totally understandable. I sort of like, so okay, caveat here. I'm gonna go on a minor rant on education type stuff. I was a teacher. I taught programming type stuff. I think that most books and most people get education wrong, where they try to teach you like theory first, and they're like, here's the theory of how all like the memory and everything else works. When, in my opinion, and also there's some science backing this up, going practical first, just like, here's something, do it. Works a lot better. And then later on, okay, now that you've done it a bunch, let's go into the theory and like how that works so you have the context to understand it. You want refinement types in Rust, so Rust can get close to AGDA and Idris. I'm not familiar with those, so I don't know what refinement types are. You prefer the programming Rust book over the Rust book. I never read the programming Rust book. I've heard really good things about it though. It's on my wish list, my personal wish list. Okay, so what were we on? This was 64, and then it would be 128. So 128 is the maximum, because everything with 7 would be 128. So if you flip that bit, it gets really confusing, right? I rotate this left. Yeah, so we get that. Oh wait, I forget, what was it? It was something like $1, $0 for position 2. Let's see, is it colon? Let's see, expected, where do I put that? You're watching Rust tutorial and you saw something that obviously worked, but because the execution things or memory, you don't know, it didn't work. Wait, you saw, oh wait, did you try to like implement it yourself and it didn't work? Or did like for the person it didn't work and it should have worked? Oh, with a refinement type, you can create a numeric type that all values are odd. Oh, so you can have types on runtime and types on type. That's interesting. Or make a constraint that a function, a list must never be empty. That's interesting. It's literally just 2 prints for the person who didn't work on purpose. So for that, the what is ownership stuff, like, so reading about ownership is probably helpful after you run into a bunch of ownership problems. Oh, come on. First time chat, well, not surprising first time chat. Also, last time chat. Okay, so you move into, okay, so we know that you're in like 111. Oh, what the hell? I have not been following Roblox at all, so I have no idea what's going on. It's been down for 4 days. Wow. Wait, oh, you're talking about stock. Okay, I thought you meant like the game's been down. Like Roblox, nobody could like log into it for 4 days, which would be pretty crazy. Oh, wait, it's been, oh, well, yeah. That's probably, that's like, what do you call suboptimal for any business? So if I do 111, okay, so my brain is like no longer working for math stuff. So let's try this. 111, 1, 2, 3, 4, 5. Let's just do this. That's 224. But in an integer, that far left one. Oh, let me take a look at that. We've had problems with links before in the past, so I turned on link protection from Nightbot. Let me go ahead and take a look at what that was. It's an Imgur link. Hold on, let me make sure it's safe. Oh yeah, it's this. Yeah, making things more awesome or making things work would be good. Yeah, totally. They have been using soap since they started. That's a decision. That's a life decision right there. Okay, so if I do 0, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5. Okay, so that's 96. Would it be negative 96? Is that would be getting negative 96? So I would not be expecting this. Okay. We'll just do this twice, right? We'll do don't be binary. Be like that. I forget how to do the positional thing. Oh wait, is it not the colon? Can I do something like $1 there? Oh, I think that's how to do it. So $0, and then you're just like that. No. Yeah, I forget how to do like the positional stuff. Nah, the syntax is odd enough, and I don't feel like looking it up. So we're just gonna copy you and do this again, but not in binary. So here, when we have 111 0000, so this is 1, 2, 3, 4, 5, 6, 7. So 7 of these. We get negative 32 because this gets moved over and we only have 1 and 1. So we have, this is what we'd be expecting. A negative version of this. But it's not what happens. It's almost like all right. It's almost like that. Almost like 2 of them got moved over. Huh, interesting. Well, yeah, I mean, the idea was, so we're gonna put in rotating left on integers is strange. Don't do it. That's all I can really like pull from that. Okay. What's next? Rotate white. Okay. Swap bytes. Reverse the byte order of the integer. Is that like the same as reverse the byte order is not making? Okay, so that's reversing. Okay. From BE. Okay, so then we have like the entire big endian, little endian things that we saw with F32s, the row. Yeah. Rotate and signed integers is strange. You're right. I should. That's the, yeah, there you go. Okay, checked integer addition, compute self. Okay, so returns none if overflow occurred. Now this is interesting because sometimes we do like a plus on something and then we don't check to see if we are like overflowing. But is there a point for this? Like if I'm doing, if I'm taking something and adding to it, wait, was there a checked add in floats? I don't remember a checked add in floats. I don't think there was. Like if I do number dot, yeah, there's no checked add. But there isn't integers. That's interesting. So if, yeah, it almost doesn't make sense for me to then use this the way I would expect it to, because normally I would like in the game, okay, we're moving, like we're adding another ball, we're moving it to the right. If it goes off the screen, great, but if it goes like too much bigger than like the entire F, for like the floats, for like, you know, whatever size we are on, F32s, let's say, then I want you to just die. I would have to do like the math to make sure that you're not gonna like go out of range of what an F can be. But if I could just do this checked, that'd be fine, except I can really do that in eyes. And maybe use. Huh. Unchecked add. Isn't unchecked add like essentially what happens right now? So, okay, here. If I do, let's do like let max equals I32 max like this. This is the largest that an I32 can be. And then I just go ahead and add one more to that. That should overflow, right? Attempted to compute max, which would overflow. So the compiler stops me and says, hey, why are you doing this? Don't do it. And then, you know, kicks me out. Can I do this in 2 lines and then the compiler won't figure it out? So can I just say debug max +1? No, it still figures out that it's going to be, ooh. It actually is checking for these overflows. Well, you know what I'm gonna do is tell it, hey, you know that all that checking and trying to be nice to me? Just allow me to be silly. And now let me die. So here we go. Here's our error. We get a panic that attempt to add with overflow. And so we get our runtime error. So if we have like static things, it will protect us when we're like have the actual code and numbers that we're creating. It's when we have numbers coming in from outside of the world of the universe that is when we can get these overflows. And so an unchecked, which is going to be a nightly thing, is going to allow us to say like, yeah, let me do it. Compiler assume this is gonna work just fine. Everything will be fine. Check sub. Okay, so same thing for subtraction. Now this returns an option. Okay, so cool thing. Now if I go back to deny. For this, let's say we have a deny and you're going to now yell at us because why aren't you yelling at me? There you go. You're yelling at me because this should not work. But if I do the checked add, so we're going to do max.checked add, and the right hand side is going to be just 1. That's going to return, it now is allowed for me to do this, and it's going to return an option with none inside saying, hey, you try to do this and you're not allowed to. It sucks. You're gonna overflow. But if I do like a checked subtract, it won't be a problem. Okay, cool. And it looks like there's all these checked, all the other math for us to do, which is nice, but I kind of wish that they have these on floats too. Does F64 have that? No, there's no check. Oh, that's actually too bad. I kind of wish that they had that. Okay, so basically just like tons of these checked, which are actually really nice to have. So like next time I'm doing stuff with this, I might pull that out. checked power. Nice. Saturating add. Saturating integer addition computes self plus right hand side saturating at the numeric bounds instead of overflowing. Wait. What? Okay, so let's try this again. So now I'm going to do a saturating add. And what is the max? So the max is this number, so 214,748,364. Oh, okay, so it doesn't add it if it can't. Okay. If it will overflow, don't increment, don't add the number. Just go to the max. That's good to know. Okay, so same thing with negative. And then just everything has saturating. Okay. Interesting that some of these are nightly only. I guess like they're still writing some of them out and testing them. There's this wrapping too now. So wrapping around at the boundary of the type. So does this mean it becomes negative? So let's say I have a debug max dot wrapping add 1. Are you going to become like the min? You are. Okay. So wraps around to the negative, like, okay, so if it overflows, wrap around to the other extreme side of the type. Okay, so then everything over here. I don't know when I would ever want to use wrapping for that. That seems a bit odd. I guess like if I do have that many numbers and I'm like, I've got something on every single one of them. Okay, what's next after all these? Okay, overflowing add returns a tuple of the addition along with a boolean indicating whether an arithmetic overflow would occur. If an overflow would have occurred, then the wrapped value is returned. The wrapped value. Oh, okay. So overflowing. So right hand side is going to be 1, and this is going to be interesting. So we get the wrapped value and true. So you're going to need that. And so in this case, we're going to get that and true. So this is return a tuple, letting us know if we are overflowing. And if we are, then wrap. What? Why? Come on. That's certainly a choice. Okay. Carrying ad. Okay, that's nightly only. What is that gonna do? Ternary addition, which takes in an extra bit to add and may return an additional bit of overflow. Okay. So we can then use big int essentially with it. Could be interesting. Okay, so then we have like the things that we've done all before with other numbers. We have like power to like raise it to the power of. We have like div Euclid. I don't know if I ever do div Euclidean division. Or just like normal division. The quotient by itself by right hand side. It computes the integer q such that self. Okay, so q times right hand side times r with r equals the remainder Euclidean right hand side. In other words, the result is self divided by right hand side rounded to the integer q such that q times right hand side self is greater than q times right hand side. If self is greater than 0, this is equal round towards 0. Otherwise, it's equal towards up above. Okay, so basically it rounds. In maybe a better way, maybe a worse way, I'm not sure. Okay, so the remainder, unstable div floor. That might be interesting when it happens. Bunch of nightly only stuff. Okay, absolute value. I mean, that's like a stable. It's also on the integers, which I think is something that like a lot of people don't realize when you're first starting to do Rust stuff is all the math things are on the actual numbers itself. So you just have the number.abs and you're fine. Okay, so signum, so it gives us like a 0, 1 or -1 depending upon what the sign is. That's actually really nice. Interesting that it gives us a number 0, which means we can't have a -0 then, I think. Or can we? I know we can have a -0.0 in floats. Okay, so is positive, is negative. Those are really nice to have. Simply because you can just avoid doing weird math things in your if statements. 2b bytes. Return to memory representation of this integer as a byte array. Okay. Very similar to like the floats. We saw those too. Okay. Min value and max value are deprecated. Now they want us to use the constant. It's there right now, but it will be removed. And then we have our trait implementations. So perfect. Now this should work with all of the integer types from I8 all the way through I128. So I'm going to go ahead and let's fix our one warning. Right, so this gives us a result. I kind of want that to show. So we're going to do allow. I don't need that anymore. This is now going to be unused, must use. So allow that. So basically, let's do same as I32 because that's what we're looking at this, but it's pretty much the same as those. It's I16 is going to be the same. Probably like same as is maybe not exactly correct. Okay, there we go. Very similar to. That's probably more correct. Okay, so now there's the I size, which I think might be worth looking at separately, because like the I size and the U size are used in sort of like different times. Although I don't think I've ever used I size before. U size all the time, because that's what you use to get into like arrays, for like positioning. So I look forward to like getting into that. However, I am gonna have to do that next time because it's 12:30. I am like starting to feel my brain fade away from all this math stuff. So I think I'm gonna have to take off for the day. Go rest, get my brain back working. I'm not having any scheduled weekday streams right now. So like the next scheduled stream is going to be next week, on Sunday. And we're probably going to continue with this, unless I have like some other thing come up, in which case we'll do that. Anyways, thank you so much everybody for hanging out with me today. I've learned a lot. Hopefully this was helpful for you too. And I'll see you all next time. Bye.